Hey, so we have been solving separable differential equations, and you should be able to look at this differential equation and pretty quickly remember that, oh, the answer to this is an exponential growth model. And we talked about why exponential growth model and population go hand in hand. But the one thing that we always kind of get away from is the fact that if we think about an exponential growth model, it grows exponentially, so there is no bound. Which, if you think about the Earth and people growing on the Earth, if we truly grew exponentially, at some point there would be more human mass on the Earth than the weight of the planet itself, and obviously that's not going to work. So there has to be an upper bound, and there was a whole bunch of people that thought about this. I know that a lot of you have been reading Walden Pond, and I think one of the peers of Thoreau was Mathhouse. Mathhouse? I don't know. And he thought a lot about this. Anyway, this is math coming from the social sciences. And so people said, it doesn't make sense. There must be an upper bound. There must be an upper bound that a population, if it gets above this, it has to drop below it and maybe it comes back up, maybe it rebounds. But it doesn't make sense that it just grows forever. So people try to think about, well, what can we do for that upper bound? And or mathematicians started thinking about that. So let's assume that upper bound is k. And let's assume that we would be happy with an equation that maybe did something like that. Well, what we need to do is say when this y gets very close to k, the rate of change has to approach 0, right? The slope over here is 0. The slope over here is 0. When y is very small, right, close to 0, then the slope is close to 0. When y gets close to k now, we want the slope to be 0. So I challenge you to kind of hit pause and see if you can think of a term maybe we could multiply this by that would, when y got close to k, this whole thing would approach, or the slope would approach 0. So hit pause, give it a try. So what they came up with was to say that we need another term, and we were going to add the term 1 minus y divided by k. So let's, I'm going to rewrite that so we can just see it down here. dy dx, the rate of change of y with respect to x, or respect to time, we could say, is some rate, some constant, times y, that's your exponential part, times this limiting factor, 1 minus y over k. And the idea here is when y is very small, when y is close to 0, this term is close to 0, so therefore this term is really close to 1. 1 times anything is just itself. So this, when y is close to 0, grows exponentially, right? However, when y gets near k, when y gets closer and closer to k, this term becomes 1. 1 minus 1 is 0. And if 1 minus 1 is 0, then r times y is also going to be 0. So the slope is then 0. So this is a logistic differential equation where r is, so this is where my previous video about mx plus b, this tells us pretty directly, this is our rate of growth. This k right here is our maximum population. Right? So we should be able to look at an equation of this form and go, oh, if I rearrange it and play with it a little bit, I should be able to pull out the rate of growth and the population like that. And we should be able to see some other things that are happening in here. If I distribute this to here, you'll see that basically all we've done is we've found ry times 1, ry minus ry times y over k. We have a derivative equal to r is a constant, r over k is a constant, a derivative equal to a quadratic. Like, that's all this is. So if we can take this and rewrite it like that, we should be able to go, oh, I know what the maximum population is, I know the overall shape of what's going on, and be able to solve it. So the big idea is that we've got a k, that there's our maximum, we have this curve that is kind of growing exponentially, and then it tails off almost exponentially in the other way. So we actually have two horizontal asymptotes that we are dealing with. One is 0, the other one is k. And we should be able to kind of see this and play with it a little bit. Yeah, that's about it. I'm going to be asking you some questions. I'm going to give you some questions where you're going to have to look at it and they're going to say, hey, what is the population growth? And you're going to, or the maximum population. You're going to have to figure out how to rearrange things so that this is a 1 and that's the answer, right? Sometimes it might say, well, what is the rate of growth? You might have to rewrite things like this and see what you can factor out for the r to figure that out. Anything else? Oh yeah, I want to point out one more thing. There is a point on this graph where it has a maximum growth rate, right? Where dy dx is a maximum. So there's some spot here, dy dx is maximized, right? And that is where the population is growing the quickest. So you might get a question where it says, hey, what is the maximum rate of growth? Well, we could do a couple things to figure that out, but all we're trying to do is find the maximum of this equation, right? So we could take this derivative, right, second derivative, but if you just call it the rate of growth, we could take this derivative, set it equal to 0, and solve for the population, x, and then you would have those answers. So, yeah, hopefully, so this might be a little bit challenging, but hopefully you can get through it and ask some questions, and we'll talk about it. Thanks. Have a good one.